This
We
conference will now be recorded.
will Dft Demo Session. Um, so myself, Vamsi, I'm the Dft trainer over here in this organization, and I have more than 10 years of experience in the field of DFT. So I will be teaching the technical concepts for the DFT here. So we will try to walk around the presentation what we have for today's session. So let me start with my agenda of the today's session. So today we are going to understand what is meant by DFT, and we will also see what are the different course topics we have in this entire course outline, and we will also see what fundamentals are required for any individual to start the DFT course. So we will also see there are some specific tools, EDA tools, the design automation tools, some online softwares were available, offline and online. So we will try to understand how these tools will be useful, and how using them, how do we implement the tasks which are related to the DFT. So we will also discuss about the projects and the lab sessions, how we are going to support in terms of the practical session. And as usual, some placement opportunities also, and how do we share the materials during the course duration. We will discuss about that. So these are the couple of points which I have put into to discuss as an agenda for today, to make you understand what is meant by DFT and how it plays an important role in the entire flow of the VLSI. So the first slide which I want to start here is who all can attend this course. So many of you may have some questions or some queries whether you are eligible to take up this course or not, whether whether the course is really suitable, or whether it is relative to your particular current situation or not. So I have listed some points here. I hope everyone, right, you will be fitting in one of the points which I'm trying to tell here. So the first point is any student who are in final semester who are seeking for the DFT course as part of their course curriculum can attend this course. Or any NCG, a new college graduate who is from the relevant branches of engineering and science, can also attend this course. It will be helpful for them. So even the lecturers and professors who want to switch their career into the real-time industry experience. So imagine you are a candidate where you are working as a professor in some organization, and you want to come out of the teaching field industry, and you're more passionate to work towards the real-time market industry of VLSI. Yes, the course will be really helpful for them too. And finally, even the working professionals from similar or from other VLSI domains. So whether if you are a working professional who want to switch your career into VLSI also, this course will be helpful really to understand what is meant by DFT and how it will be benefitable in the entire cycle of manufacturing the chip. And it can be other domains also, like imagine you're already a working professional in VLSI, not in DFT, but imagine you're working in some other domain called as physical design or verification or some other domain, and you are interested to switch into the DFT domain. This course will be for sure will be helpful. So we are planning for overall 16 weeks of duration, approximately. It may be varying plus or minus with margin. It can extend up to 17 or 18 weeks, or it can complete in 14 to 15 weeks based on the interactions we are having in the duration of the course. So there will be theory classes on the weekends, and the practical sessions will be conducted on both weekends and weekdays. So there will be different types of batches. You can check with the admin. So some batches will be divided in the weekends, some batches divided in the weekdays, only for the practical sessions. All the theory classes will be on the weekends only. The main theory, the core DFT theoretical class will be on weekends. So I would be linking the theoretical and practical together So it is something like we pick a topic, we understand the theory, and we try to analyze that in the practical sessions. We complete the topic, and then we go for the next topic for the theoretical concept. So all the courses, all the topics which are outlined in the course outline will be presented in the next slides, where I'll give you some introduction about how and where this DFT is involved and how it is beneficial. So the final thing is like the developing your personal analyzing skills. We would be conducting some interactive sessions, interactive assignments, some quizzes and all to keeps you motivated in order to not losing the track of the regular sessions. It will also improve your personal skills in terms of like the communication and other skills, as we will also be helping in conducting the mock interviews. So what are the skills you require to start a DFT course? So what things you have to be prepared first so that we can kickstart or we can jump into the actual main core topics of the DFT. Let me write it out few here. I have already presented. So the first thing is like you need to understand very in detail about the VLSI design flow. So there is a design flow for this VLSI. So you need to understand the design flow. How does the flow start? So if some company or some person want to create a chip, create an IC, an integrated circuit, what is the flow? How do we follow that? It's called as VLSI design flow, or also called as ASIC flow, which in terms specifies that application specific integrated circuit flow. So you really need to understand the flow that majoritarily speaks about how many different domains are there in VLSI for making a chip, and which domain comes prior and which domain comes after. How does the flow of work follows in the entire design in the VLSI? So you don't need to worry about if you are not aware of such design flows. As part of this demo session, we are going to discuss about the design flow in a brief way. So in the next few slides, I will be explaining about the VLSI design flow for you. So the second important point in the skills required are the digital design and the basic electronics. So I hope irrespective of your department of education or your current working profession, if you are related to the engineering and sciences, if you have done your bachelor's or master's related to engineering and sciences, you would be knowing what is meant by digital design and a basic electronics. So a very basic understanding of these two concepts are required. And as we are going to use these designs, which are called as circuits, in the entire course duration. So digital design and basic electronics are mandatory for any individual to understand before starting this course. And you may have a question, how far you need to ramp up really on these topics? Is it something you need to do some R&D on this work? Not exactly. You need to just know the basics of this. So the digital design and basic electronics, you just need to understand the very basic conceptual concepts. Something like what is meant by a flip-flop, what is meant by a combinational circuit, what is a truth table and characterization of a logic gate, and some other things. Like if you are comfortable, you can also learn about some basics like what is meant by a state machine. For example, we have some finite state machines to detect some numbers, right? Like 101, 010, how to detect a number using a state machine. Of course, you need to understand about some other circuits, like what is meant by a divider circuit, what is meant by a adder, full adder, subtractor. A very basic understanding of conceptual is very good enough here to kickstart the DFT course. So the third important thing is the Verilog language. So Verilog or System Verilog or VHDL, any one of the language if you know, that should be sufficient and good enough for us. Out of which the most priority language is a Verilog, a simple and structured language that speaks about the coding of the design. How do we build up a chip, right? So Verilog is a language that describes the circuit behavior. So in this Verilog also, do you need to code anything? Not exactly. We are not going to code anything using our manual efforts. We have some tools that can actually write out the design code for us in the DFT. But you need to understand the Verilog code so that if a tool writes a code, you have to open the code and understand what it has written, how it has connected, what is the communication it is doing between some instances. So you don't need to do any PhD in this Verilog, just a basic understanding in such a way, open a Verilog code and try to understand the structure is 99% good enough for us to complete the DFT course also. Okay, so don't get afraid like you need to understand the coding structure too much. Understanding is enough. You don't need to write any code here. So some basic EDA tools are also available. So you need to understand about them. You might be using some of the tools like C. I hope everyone is aware of C language or C++, a software tool that does multiple operations based on the user instructions. So here in the VLSI also, we have some EDA tools that performs the operation based on the user instructions. So we call them as the design automated tools. Okay, electronic design automated tools. So the tool does the job in a faster and simpler way based on the instructions what we give. So we play around with the tools, the software tools what we have for this implementation of the designs. So we will be helping you in the understanding the tools during the course duration only. So you no need to worry about this point also, as it will be covered by default in part of the course during the course duration. Anyway, the first point I have explained that today I'll be taking it up. So the remaining 2 points are something I'm expecting from each and every individual. Now we have something called knowledge of C and also some scripting languages like Perl, Shell, and Tickle. So these languages we are recommending the candidates to understand again the very basics. We don't want extraordinarily the in-depth of these conceptual languages. We just need only very basic things like the syntax, how what are the different syntax available in these particular languages. So why do we need these languages? As the EDA tools, what you have seen in the above point, are more precisely built up with these languages. So if you know the language in a better way, even at the basic syntax understanding, you will be able to easily handle the tool which we need to use it for the implementation of DFT. Okay, so these are all the only basic skills which I'm proposing like each and every individual should have, out of which the first point will be taken care by us, even the third point will be taken care by us. The fourth and fifth, I will also try to cover some part of the scripting languages in my duration of the course also, so which are very basically required for the DFT. So the majority of the point what I am expecting from each and every individual is the digital design, basic electronics, and a very basic understanding of the Verilog. If you know these two basics from your end before you start the DFT course, it will be very easy to correlate the concepts and try to understand them. Okay, you guys are able to follow me? Does anyone has any questions? You can chat with me, or you can enable the mic and answer. Sorry, put your question. I can answer that. I see like 14 to 15 people are online today. Let me know if you have any questions on so far what we have discussed. I can take some pause, I can take some break in between to answer your queries and all, and then proceed or continue the next slides. You guys were able to follow?
Hello,
Everything is
sir.
fine till now. Okay, struggle. Yes, go ahead. Yes, Abhi.
Sir, I want to ask a doubt.
Yes,
Sir, right now you told that scripting language like Perl, Shell, and TCL, are
yes,
these important to, are the knowledge of the basic knowledge of these scripting languages
yes.
important to handle the basic EDA tools?
Yes, it is very much important because the tools will have their own commands and switches and their own syntax. Mostly, some of the commands are 99% correlevant to the one of the scripting language here, which is called as Tickle, which is TCL. Okay, for example, I would like to load the design into the tool. So I would like to set a variable to design the load to load the design into the tool. So how do you set a variable? It requires some scripting language. For example, in the TCL, there is a command called set, set. So if you do not understand what is meant by a set command, you will be finding it difficult in understanding the tool commands.
So,
Did
sir,
I answer your question?
sir, yes, sir.
Yes.
Sir, what are the basic EDA tools that we are, as an DFT, to learn about EDA tools? What are the basic EDA tools?
So there are some basic EDA tools, like for example, you have Verilog simulators. So you need to understand what is meant by Verilog. How do you write a test bench for a Verilog? How do you get a stimuli of the Verilog? Right? So there is some website called EDA Playground where you can get some online simulators, online EDA tools, where you can copy some code, execute some code, understand the output of it. So these are nothing but the basic EDA tools which I have mentioned here. Because imagine a person who is not at all aware of any software language or any software tool cannot directly jump into the course. I hope everyone will be seeing any some software tool across the your journey of your education. I agree that, but what if a person has never seen a tool that which involves with some instructions and get an observe an output and get the result, right? So in order to cover the topic, we have written here like some basic EDA tools, understanding and some utilization is required that you might already have your during your graduation. That will be very well and good. That makes you that comfortable in using new tool or when we teach the new tool.
Okay, yes, sir. Thank you.
Okay.
Yes, sir.
Okay. Any other questions from anyone else? I see like three persons have responded in the chat window to me, like they were able to follow the current session. How about others? Okay, fine then. So let me continue. Let me go to the next slide and we will try to see what all the things we have here. So as we are speaking about the VLSI design flow, the VLSI design flow, right here which you see. So let's try to understand something about it. If you are already familiar about the ASIC flow, it is very well and good. But people who are not aware of what is ASIC flow or what is VLSI design flow, if you are hearing for the first time, it will be very interesting. Let me try to explain you some key points about it. So VLSI design flow is also called as ASIC flow. The ASIC here, ASIC stands for an application specific integrated circuit. So integrated circuit here is nothing but a chip, what we call, because the entire digital environment is built up with some chips and some boards, right? So the chip is also called as an integrated circuit, which means some n number of components, m number of some gates, or n number of some device which is built into it is integrated into a small area is called as a chip. So if the chip is working for a specific application, we call that as a application specific integrated circuit. So how do we build up a chip based on some application? How does it happen? What are the steps we have in the global or a top level overview we are just trying to see now? So the first and foremost thing is a design specification. So if you want to build up a chip, if you want to produce a chip, if you want to get a chip into the market, if you are designing the chip, you need to understand what all the specifications required for the chip. Are you going to build a chip that should be supportive for some automobile industry, or it should be supportive for some digital environment, something like a digital camera or a digital gadget, something like a smartphone or a laptop or a processor, something like that, an artificial intelligence chip, or it's something used for some internet of things? What kind of application? Or is it something simply will be useful only for a Bluetooth feature or an audio feature? Something, any digital market or any digital instrument that which involves in the digital circuit you need to understand a specification before you start a chip. So there would be a separate team called as a design specification team in most of the companies, in some like MNC companies and all. If you go for a small scale companies, even the designers will act as a design specification team. So what is this team does is right. They collect the information of what all such components are required as per the customer requirement or as per the chip which they want to produce into the market. For example, a company wants to produce a chip, or a country is planning for a IC, an integrated circuit, which is required specifically for a health sector or some defense sector. So they need to understand what all components to be placed into it. So the first and foremost team here we call that as design specification team. Once the specification is decided, then we go into the next domain called as a design code. So far you got the body of the chip, which means something like this. We understand that there will be a chip, there will be some blocks here, there will be some structurally box, something like this here. So everything will have some circuit. So for example, this circuit will be useful for USB. You'll be having a USB port into the processor or to the board or something like that, right? So this circuit acts for the USB protocol, what we have. So once the specification is set, now the design team will take the same specification. They will start writing the coding. They will start writing the coding here. So we call them as RTL design engineers. We call them as RTL designers. What is meant by RTL? Can anyone tell me what is abbreviation of an RTL? What is an RTL?
Register transfer level.
Okay. Why do we call that so?
Because in this any hardware.
Yeah. Go ahead.
Hello.
Yes, yes, go ahead.
Because in this any design is as hello.
You're audible, Abhi. Go ahead.
Any design is assumed to be seen as a combination of flip flop, two flip flops connected with a combinational circuit. So we are transferring data from one flip flop, that is one register, to another register. That is why we are calling it as register transfer level.
Okay. Yeah, your answer is true. If the communication of data transfer happens between the register to register, we call that as register transfer level. Okay. So the people who writes the code can also be named as the RTL designers or the front-end designers of the chip. So once we have the design placed, we have, so by the way, this design code can be in different languages. People can write it in Verilog or VHDL, or they can write it in some other language also as per their requirement and their as per their specifications what they have. So once the design code has been written, there should be someone who has to verify or validate it. So we have a third team of engineers called as verification team who does the verification of the chip. For example, they have written a design code for a full adder here. The designer has written a design for full adder. So you might be knowing what is a full adder circuit. Ideally, it's a very small circuit I'm taking for an example, but in the real time, people write the code for some microprocessors, controllers, and very complicated chips design. So there will be a separate team who will be validating this code, which means the verification team will start validating the design by doing some validation. We call them as validation engineers. So what they're going to do, they're going to take up the chip, they're going to apply the stimuli, input stimuli. They will see whether the chip is working properly or not, or whether the chip is working. The correctness of the chip will be checked by the verification engineers, which means that whether the circuit is as behaving as per the specification, which is full data or not. What if it is not behaving like a full order? So they will try to validate it using some test cases and try to understand that they are trying to maintain the same specification which is followed by the previous team. So if the design has been validated in the early stage of here, then what else the other domains we have? Now we have a next domain called as synthesis. A synthesis is a domain which is again related to Verilog code. Synthesis is a domain which is again related to a Verilog code. So what is a Verilog code? Which we already have in the step number 2 here. In the step number 2 you already have a design code which is also nothing but a Verilog code. So the designers here, where we call them as RTL designers, will be writing the design in the behavioral code itself. They have different types of modelings, right? They have different types of modelings in the Verilog, like data flow modeling, structural modeling, gate level, or behavioral modeling. Different types of modelings are there. So it is very easy for the designer to write a complex codes in terms of behavioral code, that because they use some functions, some parameters that can be easily called or can be reused from one code to other code. So they most precisely they will be writing the code in the behavioral mode. And what does this synthesis do? All the behavioral code will be converted into the gate level code. The same Verilog code will be converted into the gate level structural code, which means you will be able to see the physical AND gates, OR gates, multiplexers, flip-flops, all the physical instances you can clearly see in the code rather than writing a Verilog code in the behavioral type. So the behavioral code will be having a structure like always statements, or a begin statement, case statements. That is the structure of the behavioral code. When you go to the gate level, each and every net connection should be represented, how the connectivity is there, from what instance to which instance it is there, in a detailed and structured way, which we call that as a gate level. So we have a separate tool that does this operation to convert the RTL behavioral code into the gate level Verilog code. And why is it required? When you want to go for the manufacturing, if I give always statement, if I give something like assign, something like this, assign C is equal to A into B, the manufacturer doesn't understand what is this A star B, which is nothing but a simple AND gate. So they will understand, okay, there is a pin called as A, there is a pin called B, this is C, and this is a physical representation of an AND gate. So by looking into this instance, people can understand, or while manufacturing, they need this. So for it's a mandatory process that we have to convert the behavioral code into the gate level code. You may have a question, why should we have a separate tool to convert this? Can't we sit and write it? Yes, it is possible to sit and write it also, but it is not possible for higher and complex designs. If I have some 10 gates, if I have some 10 flip-flops or 100 flip-flops, we can write it. But if I have multi-million flops, if I have multi-million gates, how do I sit and write each and every instance and net connection? It's really tough and very difficult. So this there is a separate team, or there will be a separate domain called a synthesis that can convert the behavioral code into the Verilog code. So after synthesis, we call our domain called DFT that populates now called as a design for testing. What is this design for testing? There is a keyword called test here, and there is a keyword called design. Yes, that speaks and tells that completely. You need to have some designs for testing also, which means imagine the RTL designer here in step number 2 has given a code of design and we are manufacturing it. That cannot be straight away plugged into to test and validate and verify it. So what do we need to do? We need to have some additional design in the chip. We need to have some additional design in the chip that enables the testing. What is this additional logic required for? This enables the testing. Are you testing the chip? No, we are not testing the chip. We are also designers, like step number 2. This is step number 5. Like step number 2, like step number 5, which is the DFT team. DFT team also can be considered as designers, as we are also going to write some extra circuit or additional circuit into the design that is purely will be helpful to enable the testing of the chip. So the team has been evolved as TFT, alias designed for testing or testability. So we are responsible to add the additional circuits into the design, into the system, or into the chip that is clearly responsible only required for testing, which means you're not going to verify you're not going to validate any functionality of the chip, whether the chip is working as some divider, whether the chip is working as a multiplier circuit, whether the chip is working as a adder circuit or some processor circuit, whatever it is. We are not going to validate that. We are going to add an extra circuit that enables only for testing purpose. So once this design has been added, right? Once the design has been added, which means that now the complete design, all the chip information has been added into the, all the design modifications and everything has been done. Now what is the next thing? Once the design BFD has been done, we have a next domain called as physical design now. What is this physical design? So far whatever I have discussed here in step number 1, we add the design which is required for the circuit behavior functionality. He, of course, this is verification, this is conversion of the behavioral to gate level structural code. And in the fifth step also we add some extra designs. So here and here we're adding the circuits. Once the circuit has been added up to here, then what is the next step? Physical design. So physical design is nothing but doing the layout for the existing circuit for the physical manufacturing. So there'll be a separate team called physical design team, also be called as backend team. So what they're going to do, they're going to do the layout of the chip. So they're going to take all the circuits what we have and they're going to do the layout of the chip. So once the physical design has done the layout, it's a multi-process. The layout is a multiple process. It's not a single step. They have multiple um, sub steps, I would say, like floor plan, placement, routing, and different things are there. So it's a very lengthy process. It's not that quick and cakewalk process step in the entire VLSI flow, because how many number of multi-million instances and gates you have, each and everything should be placed on a closed die area on a software, and they have a lot of rules to check, they have a lot of conditions to validate. Finally they will complete the layout design of the chip. So once that is done, we go for a sign off, where here the timing of the chip will be covered, because you need to understand the performance of the chip also, right? So the timing will be checked here, whether giving a proper signal at the input of the chip, how fast is the performance of the chip. In a way it is calculated after how many number of nanoseconds or how much of time it is taking for the signal to propagate from the input to the output, either at the chip level or at the instance level or at the gate level. So in this sign off we will have DFT work also little bit, because we are adding the circuit here. Yes, we want to validate our circuit here also. Whatever the circuit we have added, we want to validate that. So during the sign off stage, we can validate the DFT circuit which we have added in the implementation phase. So during up to this first column, I could say it's implementation phase. This is implementation phase. Implementation of the circuit. Once the implementation adding the circuit is done, we go for the layout. Once the layout is completed, you can go for the DFT validation and other validations which are available. It's a very simple categorize what I'm trying to tell here. So once the DFT validation is done, we go for the final step called as tape out. So tape out is not a separate domain. It's nothing but giving the entire database, giving the database to the manufacturing. We call that as a tape out. Giving the database to the manufacturer to start manufacturing, we call that as a tape out. So it is pretty simple, straightforward only. If you see this flow graph of the ASIC flow, how do we build up a chip? We have the implementation, we have the layout, we do some checks called as timing and other validations, and finally we give the design database to the manufacturing unit. Okay, so I hope you understood the overall topic of the ASIC flow, how it will be, how the flow graph will be there in order to complete the chip designing or implementation. So all these works will be done in the software tools what we have. So we have each and every domain will have their own software tools. like DFT has their own software EDA tools, and the synthesis has their own software EDA tools. Physical design also has, the timing analysis team also has. So likewise, every domain will have their own set of EDA tools which are built up. They will use them in the industry across the projects in the company, and they're going to utilize them and complete their task in a shorter interval compared to a manual effort. Okay. Any questions you have on this slide?
Hello, sir.
Yes. Tell me.
Sir, actually, it is not clearly audible, sir. Somewhat disturbance is there.
How about now?
Hello, sir.
Yeah, tell me. Are you still hearing the disturbance?
Sir. Somewhat disturbance is there, sir. And your voice also like breaking down in the middle, sir.
Okay. How about now? Is it better?
Now it's fine, sir. Everything is fine, sir. Now clear, sir.
Okay,
Now.
I moved my mic. Okay. The ASIC flow. So the design specification, the design code, verification, synthesis, and DFT implementation comes into a single category called implementation. Phase one you can consider. The second phase is the physical design, that which the people do the layout of the chip, and then finally the sign off where the timing analysis and some validations or works also will be done. Finally, we give the tape out. Tape out is not a team. Tape out is nothing but handing off the database to the manufacturing unit for the purpose of to start the manufacturing of the chip. Okay. Okay, let me continue then to the next slide. So what is DFT now? Let's go a little bit in depth of DFT and try to understand what is it. Yes, we are designers where we are going to add some design which is specifically required for testing. So I have a scenario here where the design engineering team, which means the RTL team, is stating that they have 20 years of experience in writing the code for the functionality of the chip, and they expect it is 100% correct. But still, after manufacturing, the chip is failing. So at the chip got failed on silicon. So silicon here speaks about the manufactured chip. So silicon here is nothing but the manufactured chip. How does the silicon looks like? Have you ever seen what is meant by silicon? It's a material that is extracted from sand. I can show you something like this here. I'll show you something like silicon ingots, which are available. You're able to see my screen, right? So you should just go to Google and see what is meant by silicon ingot. I don't want price, just a silicon ingot. So how does the silicon material is utilized for the chip? So you have some beautiful diagrams here. If you see, there is some melting and seeding options here, what you see. So there will be a seed crystal that will be put into a very high temperature container, and using the some process they're going to extract the silicon, where you can see the final silicon will be looking like a big a rod kind of thing, that which is called as ingot. And this ingot has will be cut into some slices. So the people will be cutting them into some slices, the ingot will be cutting into some slices. So each slice will be looking like this, a, a thin plate kind of thing, what you see. It will be looking like this, a slice. Yeah, this is the best example I would say on the right hand side. A single crystallization is be done. There are diamond blades that cuts this into some multiple wafers, or also called as a die. So each slice, so slice here is nothing but looks like a plate. So each slice will be again be used with the for the manufacturing of multiple chips, which means one single wafer. This is called as a wafer. So one wafer will have n number of chips which can be manufactured at a time. So each square box, what you see on the screen in any of this image, represents one chip or a processor that has been required or that is being produced from the manufacturing. So you can see some examples on the right hand side also. So they take some pieces, they cut into small pieces in square boxes from the die, and they give it to the packaging. Once they once they go for the packaging, finally you will be getting an IC, which is an integrated circuit. Okay, so the silicon is nothing but the chip what we have here. So the designers are very confident, they have written the code 100% correct, but still the chip is failing, so they don't know what to do. So what could be happening? Yes, there can be some manufacturing defects that can be occurring while manufacturing, because manufacturing is a very big unit where the very sophisticated environment will be there to manufacture a chip. Very huge current is required, a very hygiene environment is required. Even a small dust particle surrounding, I mean, which is revolving and then occurring during the process can damage the fabrication or manufacturing of the chip. So there is more prone, you may get some defects when you manufacture a product. So here the chip is also a product. So if you try to do manufacturing, there can be prone to defects. So your design code is proper when you have written it in the software, but when you manufacture it, the design has been disturbed due to some reasons. We'll see what reasons it can be. Next coming slides, I have very few examples listed to tell what could be the reasons why there could be a manufacturing defect. Now, who is going to identify this? Yes, if you start perform the testing, it can be identified. So once the manufacturing has been done, if your testing happens, then we can identify such things. Then who is going to do or perform the testing? A test engineer will perform the testing. There'll be some test engineer. A test engineer can perform this test. Again, are DFT engineers are same as test engineers? No, we are designers. We are not testing the chip. Which means that if a test engineer want to enable the chip for testing, they need some extra circuit. That circuit is being designed by the DFT engineers. So what is meant by testing? It's a process which determines whether the device is good or not. A simple terminology. So we give some input values here. We observe some output values here. We compare them and we see whether the value is proper or not. Whether the value is proper or not. So what is the value you are going to give? Based on which circuit? Based on what type of design? Yes, the DFT engineer will come to know that because they are going to add some extra circuit here as I told. So what circuit we have added? So for that extra circuit, what input you need and what output you need to observe? The information resides with the DFT engineer. So once you give that information to the testing team, they will just apply the values on the tester and they will see whether they are getting proper output or not. Okay, so we are not same as the testing engineers. We are completely different from test engineers. We are helping the testing team to make the test a faster way by adding an additional circuit into the design. So we are technically designers for the chip, but which is specific only for testing. So we are going to see what all the course modules we have here, which we are going to discuss throughout the duration of the course. So I have something called DFT architecture. Since you are going to add some additional circuit into the design, you need to understand what type of components you're going to add. We can't simply tell that, okay, let me add some 10 gates, let me add some 10 flops. It cannot be like that. So you should have a structural way. So as we need to follow a procedure. So here the procedure is follow the architecture which you are going to design based on the requirement. And what is the requirement? The first and foremost architecture concept is scan insertion and compression insertion. And what are these two required for? We add extra circuit. We add extra circuit that can test the flip-flops and the logic gates. So to test the logic gates in flip-flops, right, we have a concept called as scan insertion and compression insertion. So these two are insertion. When I say a keyword called insertion, you're going to add something extra. You're going to add or you are going to insert something new. So the concept name is scan insertion and compression insertion. What else we have? We have something called as OCC, which abbreviates on chip clock controller. So we add an extra circuit here to control the clock. We need it as clock is a heart of the sequential element circuits. So we need to properly control the clock of a flip-flop or any state element. So we have a separate logic or insertion called as OCC insertion. So this is not like testing anything. You are going to control the clock. So it's called as a controller. This is also an additional circuit that can test the flip-flops and gates, the scan insertion compression. What is ATPG? ATPG is a pattern generator, automatic test pattern generator. So once the extra circuit is added, we are going to generate some test cases and validate it in the software first. If it is passing, then the software response, what we have, the golden response, I would say, is nothing but your input to the testing team. This is the golden vectors, what we call, or the golden patterns, what we call. This you are going to give to the testing team. So that test case also we are only going to provide. And for such multi-million gates and flip-flops, are you going to write it manually? No. We have automated tools. We have design automated tools that can help us to complete these operations. Like it can add this extra circuit, it can add this extra controller logic, it can generate these vectors for us. So we need to properly enable the operation which we want to do it out of the tools what we have. And finally we have to validate it and then provide it to the next team. It can be design. If you add it, we give it to the physical design team. If it is pattern generator, we generate the vectors or patterns or test cases and we give it to the testing team. So before giving to the testing team, we validate them. We can also validate the patterns what we have written. So that is called as simulations. You simulate, which means you apply a value on the software which the golden vectors has been written, and you observe the output and see whether it is proper or not. So once the simulation, there are other couple of items here. One is MBIST, which stands for memory based. Even we know that the memories are the very crucial important components in the device. Of course, they are related to analog, but we have a method in DFT, like we can even test this analog component, which is so called as memory. So further, we have an extra circuit called as built-in self-test. Built-in self-test is an extra circuit what we are going to add. Since it is related to memories, it's called as memory based or MBIST. So this is also an extra circuit. This is also an additional circuit. Likewise, we have something called as a JTAG, or it's a standard protocol developed by few engineers and group of people. We'll come to that. More precisely, this is a protocol. It's a design only. It's a standard protocol. It will not change its function. It's a standard protocol which is across used. It is a standard protocol which is used. And why do we need it in DFT? Because this is used to test the inputs outputs of the chip. Because what if there is a manufacturing defect in the inputs outputs of the chip, which we call them as IOs, inputs outputs, which means ideally there'll be the boundary of the chip. You have inputs here of the chip and you have outputs of the chip here. So what if there is a defect on the input which is driving the data into the chip? So who is going to validate it? Yes, we have a separate logic called as B scan, which we call that as a boundary scan. So these two concepts are interlinked. Using the JTAG, we use something called as boundary scan. That using the JTAG protocol, you can test the inputs and outputs of the chip. And then We have something called as silicon validation. We will be discussing it based on the timeline of the course. What is silicon validation? Once the manufacturing has been done, what is the steps and process what the testing team will be doing it? The tester team, how they are going to. Silicon means already manufacturing has been done, which means now you are going to start validation and testing on the tester. So if the testing team wants to start the validation, so what is their procedure? How your golden data will be useful for them? We can see those steps also at the end of the duration of the course. So most precisely, we have added the maximum components which are required are very important as part of the DFT course here. So these are all the outline of the course modules which I would like to express here to tell that these components we are going to discuss for the next few months. Okay. Now, what is meant by a defect? Because earlier I have mentioned like there can be some manufacturing defect here. So during manufacturing, how does a defect occurs? What is called as a defect? If something is wrong or something is imperfect, if something imperfection happened, we call that as a defect. So in this chip manufacturing, what do we call that? What scenarios we call that as a defect? I have a couple of points here, very minimal points have listed. Some of the points are called as point defects. And what is meant by point defect? We can have something called as scratches, a metal scratch. What is meant by metal? Metal is a material that is used for the connectivity of one instance to other instance, which means I have a wire connection here between one instance to other instance. They use a material called as metal for connecting these two instances. What if there is a scratch? Then what happens? The data will not propagate from this first AND gate to second AND gate properly. It is a defect for us. The second thing is missing or dark vias. Vias means you can have a node connection. Net can be split into multiple other nets like this, which means there is a node connection here. You know what is meant by net and node? Node is nothing but having two wire connections together from one source. Of course, it's not a contention, but a regular valid source. What if this node is missing? It can also lead into data corruption. So poly is another material that is used for between gates. If you go to this internal to the AND gate, you will have MOSFET like this. MOSFET will have some terminals like the drain source and gate. So the connection between the terminals will be used by a material called as poly layers. And what if they have some cracks in that? Then the functionality of the MOSFET will be not as proper as required. There can be some bridges also. What is meant by bridges? What if there is a short connection like this? What if there is a short connection between two outputs? This is a short connection between two outputs. So likewise, many components, many things can be considered as a defects here. I have listed only few. If you see on the right hand side, there is a break in the metal connection. There is a break here in the metal connection, or break in multiple metal connections, or some metal connections got short, which means two net connections got short. Right? Some solid particle, some dust particle or some solid particle has been evolved during manufacturing that can cause like this. So some breaks or short connections can be happening like this also. And there can be some corrosion effect. What if the metal property is broken in such a way the metal is having a corrosion effect, which will eventually result some breaks. So many types of defects can be possible during manufacturing. All these will be leading to a wrong output or a wrong functionality of the device. So it's very important during manufacturing, we should not have any defects. How do you do? How do you verify it? You need some extra circuit. Who is going to add some extra circuit? DFT engineers are going to add some extra circuit that can be enabled during testing to identify such type of defects. So this is the flow of DFT what I have. So far whatever we have discussed, I segregated into some three steps: insertions, generation, and validation. Insertion is something like you add the extra circuit. Generation is nothing but you generate the patterns or test cases, the golden vectors. Validation is something like you simulate them. you validate, you verify them before you give them to the tester. So I call the flow of DFT into insertion, a generation, and then validation. Okay. So how do you categorize the defects? So now you understood there is a break connection or there is a short connection. How does your software is going to understand that? So the vector or the test pattern what you're going to write and give it to the testing team, how do they classify and tell there is a manufacturing defect where there is a short connection? So we categorize the defects into some fault models. The faults which the faults due to the nodes that are stuck to 0 or 1 are called as stuck at fault model, which means imagine I have an OR gate. The OR gate output is going to a flip-flop. I'm considering the D flip-flop here, and this connection, the OR gate connection which is going to the flip-flop, accidentally, unknowingly imagine the output of the OR gate is short connection to a ground. Then what happens? The OR gate output will never travel the data to the D pin. In fact, the 0 data will be going to the D pin, which means it will be always having a value of 0. It will be driving a value of 0. So this node or this net or node is stuck to a value called as 0. So we call this as a stuck at 0 fault model. The manufacturing defect here it is considered as short connection to ground. But in a fault way, in a modeling way, we call that as a stuck at 0 fault model. The same thing, imagine some net connection got connected to power supply like VDD. We call that as a stuck at 1. These short connections are not intentional. They are not intentional, which means we don't want to connect them. These are not intentional. We don't want to connect them, but during manufacturing there is a short connection which happened, which means there is a defect in the device. So likewise we can categorize the defects into something called as fault models. There are some other fault models also. This is not a manufacturing defect, but this is something related to delay of the design. So we told there will be something called sign off team where they do some timing analysis, right? So in testing also we can see up to some extent we can tell that whether the delays in the design are proper or not. So we have a separate fault model called as delay fault model, and this is not a manufacturing defect. This is not a These are not manufacturing defects, but still we can cover in part of testing because they are mainly related to manufacturing defects, but still we can cover them as we can try to evaluate some delay of the design in terms of testing also. Now the third one is path delay. So path delay is also a subset of gate delay again. So I'll explain this in detail what is meant by path delay, but this is also a type of delay testing what we have, which is related to the delays of the gates, the delays of the flip-flops, and the delays of the net connections what we have. So it is a subset of the transition delay or the gate delay model what we have. And what is slow to rise? Slow to rise stands for there is a delay in the design. So the transition of a signal is little delayed from slow to rise, which means 0 to 1 transition is called slow to rise, and 1 to 0 is called as slow to fall. So this part of delay is occurring some disturbance or the performance related issue. So the delays can be little evaluated up to some extent in the transition delay fault testing during DFT itself. Ideally, you can never expect a 90 degrees of a signal like this. Practically, there'll be a slight delay, right? So these two comes in the category of delay testing. They are not related to
Sir,
manufacturing defects.
sir,
Yes.
I have a doubt.
Yeah, tell me.
Sir, this slow to rise and slow to fall fault. So it is equivalent to what say rise time and fall time only.
That is true. Rise time and fall time, but rise time and fall time of the signal, absolutely, but still there is a specific condition, the rise time and fall time under some condition, or I would say under
So,
specific, let me complete it, under specific window of condition we have. So we call that as slow to rise. Okay.
so yes, sir.
Okay.
So I should infer from this is the amount of time that actually that should be the actually that should be actually the rise time. What actually should be the rise time of transition from 0 to 1, but more than that time period, if some gate is taking time to go from 0 to 1, if more than that, then it is called
Yes,
STR.
correct. You're right. In under specific window, which means the your statement validates at a specific window of time in the waveform what I have. So ideally,
Yes.
I launch the data, I capture the data, right? So the capturing the data will have a specific window of the time waveform. So during this waveform, when it is captures, then during that time, what if the delay is occurring little bit like this, or if the delay is occurring like this, my data capture will not happen within the time what I have. Okay, it may not impact the driving circuit in terms of logically, but in terms of the delay it affects. So my capture window is only this, which means I have only one capture window like this here, something like that. So within this duration of the window of condition, my delay of the data should be also accumulated, and it should be coming within the proper time. Did you understand the point?
Yes, sir. I got.
Okay. See, we are trying to borrow some verification concept, but not 100%. Okay. So once this is done, the fault delay of the transition and path delays, we have another type of fault model called as IDDQ, which is called as faults due to leakage current. So you might be knowing that the MOSFET will have something called as secondary order effects, right? So one of the secondary order effect is nothing but leakage current, which means dq here stands, IDD is nothing but the drain current, q stands for quiescent. A quiescent is nothing but inactive. So almost the device is been in inactive state, but there can be a possibility of leakage current. So how do we test it in DFT? Can we test the current in the DFT? 100% no, but we can help some other team to produce some vectors. I mean, we are going to produce some vectors and we can give it to some other team, which is called as IR analysis team. So the IR analysis team, taking your output as input, can try to check what is a hotspot in the design when the device is almost in inactive state. So this is also can be considered as one of the fault model, because leakage current is a very bad point. If you have more leakage current, it may damage the chip in such a way it can burn it up. So it's very important in the lower technology nodes of the chip manufacturing, the leakage current, as we go for very low voltage domains and low power domains, right? So this leakage current plays a very crucial important role in the entire part of functionality of a chip. So we do have a separate testing in the DFT called as IDDQ fault model. There is another fault model called as bridging fault model. So here I have short connections. The first one is the short connections which I have spoken, which is stuck at 0 or stuck at 1. Now this is called as bridging fault model, which means, as I just told, there is one net connection here, there is another net connection, both got short, interlinked, and they got short, which means the data is corrupted again here. So such type of faults can be identified, the defects can be identified using a model called as bridging fault model in the DFT mechanism. Okay, so I'll take a small example here. There is an inverter circuit. It's an internal circuit of an inverter. So ideally you might be seeing an inverter like this, where you give a value 0, it gives a value 1, you give a value 1, it gives a value output 0. So inverter will have a CMOS. This is a CMOS circuit what I have drawn here internally, and the output of the inverter is being accidentally tied to 0. during manufacturing. So this connection is nothing but this one. So what happens, irrespective to the value of the 0 or 1 at the inverter input, I will be always getting a value called as 0 here. Y will be always 0. I will never get a value 1. So this is a defect, right? So we have to identify this defect. Okay. So the defects can be the stuck-at fault model defect, can also the defects which are related to short connection to the ground and VDD, which is alias called the stuck-at fault model, can happen on any gate or any flip-flop. It's not only in the inverter. If you see on this example, there is an AND gate where the A is stuck to 1, or there is an OR gate where the Y is stuck to 0. So every net has a two possible combination like stuck 0 and stuck 1. So in this gate, how many stuck-at faults are there? 6 stuck-at faults are there, which means stuck-at A, stuck-at 0, stuck-at 1, stuck-at 0, stuck-at 1, stuck-at 0, stuck-at 1. So any gate of 2 input will always have 6 possibility of stuck-at faults. We can assume like that. So what is that we are doing here? We are assuming there is a fault and we are writing a test vector and we are giving it to the testing team. I'll repeat it again. We are assuming there is a fault and we are writing a test vector and we are giving it to the testing team. Okay, so if I assume a fault and I write a pattern to test that and I give it to the testing team, now two possible things I have. What if it is passing, which means there is no fault? What if this pattern is failing, which means your assumption is proper, because you assumed a fault and it happened, which means the fail occurs on the tester. You have assumed a fault, you have written the pattern, but on tester it has been passed. So we call that as there is no defect. So we write the golden vector and give to the testing team. Along with the implementation, we also do that. So there are different tools which are used in the industry. The EDA tools which we are speaking about, mostly there are three tools, vendors and companies, called as Synopsys, Cadence, and Mentor Graphics. So for each and every component in the DFT, they have their own set of internal tools. So Mentor Graphics is a vendor or a company which provide the tool, but they provide this tool called as MBIST Architect. If you want to do the insertion for the memory BIST, they provide a tool called as DFT Advisor. If you want to do scan insertion, they will provide a tool called as test compression. So these are all called as licenses. It's all a single tool. This and this one, all these are, not this one, let me rewrite. So this one, this part, and these three are single tool. A single tool with multiple licenses. What is a license? For example, you are using a Microsoft Office. Microsoft Office is a single license. Sorry, single tool. But internally you have different features like MS Word, PowerPoint, and XLS, different things you have. So likewise, this company also has a single tool that can do multiple operations. So multiple licenses are there and multiple operations can be done. So every company has their own strategy. Some companies will tell I'll give separate tools. Some companies will tell I'll give only single tool with multiple features. So it depends on company to company. So whatever the tool you pick here, the methodology of DFT is same. Add an extra circuit, make sure you get a proper pattern, you validate it, and you give it back to the testing team. The methodology is same. Only thing is like based on the tool, the syntax may be different. The syntax may be different in such a way. For example, I'll tell that in Mentor Graphics, the command, there is a command called as read underscore verilog is a command that is going to read the design. In Cadence or in Synopsys, the command can be in another way. It tells that read underscore netlist is another command. So here the methodology is same, which means you are reading the design, but the command is different. In Mentor, it is read underscore Verilog. In other tool, it can be read underscore netlist, something like that. So likewise, the commands and switches and options and the settings can be different, but end of the day, everyone follows the same theoretical concept, which is the methodology of TFT. So in the institute also, for your current batch, we are going to use this mentor graphics lesson tool, and we are going to use all these mentor graphics tools. And I'm going to explain about the synthesis also, because it is interlink of some part of DFT. I will not go for the functionality of the synthesis, but I'll explain the synthesis. We'll use this tool called as design compiler, which is provided by Synopsys vendor for the synthesis that converts the behavioral Verilog code into the gate level structural code of the Verilog. So we are going to see that. Okay. So how the lab sessions are provided here? On the following topics, we are going to discuss the lab sessions, practical sessions. So many of you may have a question. We are more speaking about the defects and the theoretical topic, how the DFT methodology work. Then what about the practical sessions? So here we are going to cover the memory-based practical session, the JTAG block level insertion, the JTAG protocol, which I told, and the scan insertion, two different flows I have. The EDT stands for the compression embedded deterministic test. This is nothing but the compression. And then the OCC insertion we are going to see. We are going to see the ATPG pattern generation and finally validation. The only thing which was not covered here from the course outline practical theoretical topic to the practical topic is the B scan, which is the boundary scan. We have something called as boundary scan, no? So the boundary scan theoretical we are going to see. Practical we are not going to cover that due to the limitation of the licenses, the tool license provided from the vendor to us. So except of this boundary scan validation or the insertion in the practically, remaining all things are already covered from the lab sessions to the course outline modules what we have discussed. So you'll be giving some access to a virtual machine called as VNC, a server virtual access to the server what we have at the organization. You can practice during the working hours of the institute. We'll give some assignments also. There'll be mentor, a junior tutor will be there who will be guiding you in the lab sessions, where we'll be practicing the entire DFT flow in the mentor graphics tool. Okay, so these experienced mentors or the tutors will be available to clarify your doubt sessions during the lab session only. Anyway, I'll be explaining the theoretical discussions, which means my session will have two things. I'll explain the theory, plus I will explain the practical session. Explanation of practical session will be taken by me. Like I'll do some lab session, I'll do some exercise, I'll open the tool, I'll show you the process, I'll do the procedure, I'll complete the task. Everything will be taken care by me. But this practical session is done by me, not by you. If you want to do a practical session, we call that as a lab sessions. Okay, if you do the practical session, it is called as a lab session. So when you do the lab session also, we have some mentors available who can help you, because they will be taking the session post my explanation on the weekends. So I'm repeating again, both the theory and practical explanation will be done by me. But if you want to do the practical online, there will be a mentor available who can assist you during the lab sessions. So we can discuss the queries and all in the regular sessions also. It is not like you have to discuss the questions only with the mentors. If you have any queries, you can always come back to me, as we can discuss them in the regular class also. So we can provide some backup classes and sessions to for the missing sessions. A dedicated WhatsApp group will be created for every batch, where we can discuss very in-depth of like the topics, queries, information, assignments, and if you have any doubts or any information related to the sessions, any issues you are facing technically or non-technically, you can use that WhatsApp group to discuss widely, where everyone will be there in the group. So I'll be sharing the materials to each one of you at the end of the week after the class via a Google Classroom. So I'll be creating a separate Google Classroom. This is lifetime validity. where you can access them at any time. I'll be posting all the materials, my explanations, notes. I'll be scribbling the notes like this. I'll be having a separate white screen of the presentation where I'll be writing the definitions, explanations, conceptuals, everything theoretical. I'll be writing some formulas, equations, or some drawings, diagrams, applying some values, everything. All my explanations will be in a scribbled notes where I'll be sharing it to you via Google Classroom. As much as possible, I'll try to maintain to very clean and neat. But still, if you're not able to understand, you can still come back to me anytime to ask me if you're not able to figure out my handwritings. So the documents related to tool commands, if anything, is available. Also, the procedures lab sessions, we will also share it via Google Classroom, or we can share it via the Medium platform what we have through WhatsApp. So I will be able to answer your questions not only on the weekends. You can reach me on the weekdays also. It is not like, okay, today there is a class happened and you have to wait for the next Saturday and Sunday. You can come and reach to me during the 5 to 7 p.m. every day, because before and after that time I'll be busy and occupied. So I have specifically arranged this slot for the candidates who are taking up this course throughout my batches from past 4 or 5 years. So you can take up this specific slot where you can call me directly if you have anything which are gated with and you want to clarify something very quick. Yes, you're open to discuss with me during these slots. Yeah, so we have different tie-ups with various VLSI companies. So there are many placement opportunities we have provided. We also do provide some mock interviews and previous questions for the preparations. It's a very small industry, but good openings and multiple opportunities would be there. So less number of DFT engineers are available, which also plays an important and key role in the entire flow of the VLSI. So number of engineers are less compared to other domains. It is not like we have less number of engineers in DFT. The number is correlated comparatively the ratio taken from other domains like physical design and verification. So DFT is involved in both front end and back end. Why did we say like front end and back end? Because here we do the insertion part, the addition of the circuit. Here we do the validation part after physical design, what I have mentioned. So we call that as front end and back end, where the DFT is conceptually involved. Yeah, so you're ready to take the DFT course. All the very best. If you have any questions, let me know. I can spend some more time to discuss and clarify your doubts and queries. Any questions from anyone else? People who have attended the course today, the demo session. Am I audible, clear to you? Have any questions? You're able to understand something like what is meant by DFT, where it plays an important role and why it is required. Very able to follow?
What about the job opportunities? It is very most of the places they are asking the experience in DFT.
Okay, so what is meant by experience in DFT? Then it is not related to this. I didn't get your complete context of when you say experience in DFT. See, any job, any opportunity in software or in hardware or
Uh,
in firmware, people
in
expect
most
or
of the
give.
places for DFT, they are mentioning that 3 to 4 year experience, like that they have mentioned.
Okay, so what is your question out of it?
So, what about the job opportunities in DFT compared to verification and design?
When you are you asking about freshers or 1 year or 2 year or 3 years or 4 years? I did not get your
Fresher,
question very
fresher.
precise.
After studying this course, we
Yes,
we, we will
yes.
be the fresher, right?
It is not like that. I'm not sure. Like, sorry, I did not get your background before I have started this course. As I told, any person can, basically get into this course, right?
Sir,
So even a same domain or there can be a DFT engineer who's already working can also attend this course.
sir,
Okay.
I
So
have a
to
doubt.
answer your question, to answer your question, Pradeep. So there are opportunities for freshers also. Maybe you have not found it in the LinkedIn or some other post, but to our organization and the institute, we are recurrently getting the opportunities for the freshers also. So in my previous batches also there are some. So all these things will be communicated via the WhatsApp groups. So we'll be sending some Google form links. asking for the candidates, telling that okay, so and so company is looking for DFT freshers, and are you interested? You can fill the form, and we forward the details to the company. They can arrange an examination or a interview, and based on your performance, people would be interested to provide an opportunity to you. So over the past three
Sir,
months, at least I have seen like 4 to 5 companies post in the WhatsApp group for your previous batch. Yes, Abhi. I think you are very hurry to ask something. Yeah, go ahead.
yes, sir. Yes, sir. Yes, sir.
Yeah.
Sir, actually, I was. Hello.
Yes, yes. Go ahead.
Sir, actually, I was having the same doubt regarding the placement.
Mm-hmm.
My dilemma is that suppose that someone is a fresher, like
Okay.
he is a new college graduate or he has teaching in some universities, and
Okay.
in case of DFT, what is happening that in the university or in even in the good colleges also, like you told that EDA tools are there and several kind of lab kind of sessions are there. Uh,
Okay.
students are students are unable to acquire enough amount of experience and knowledge in the DFT domain, like design for testability domain. People are not
Okay.
going to grab so much of knowledge and experience from the college. So as a fresher,
Yes.
when one guy comes out of the college and suppose that he has taught in some universities for 1 or 2 years, and then he is
Yes.
applying for the post of DFT engineer, like he
Mm-hmm.
don't have the much of the hands-on on the tools, but he has the basic knowledges about all those terminologies like IDDQ faults, BIST, MBIST, boundary
Mm-hmm.
design flow. Then is it possible, is it are there fair chances for those engineers to get acquired, get absorbed in the industry?
Absolutely, it is possible if you take up this course. That's why I think we are here today, right? So if you directly say that, okay, I have done some brushing up the concepts in the universities or education, that is pretty not at all sufficient if you go to a real-time industry. That's where like you are trying to seek this course, right? To understand that, okay, how does a practical world works in terms of the real-time projects and opportunities, how it will be compared to your educational qualification, the college backgrounds and all, right? So I'll give a good example. So you have something you have learned in your college or in your university or wherever it is. You might
Yes,
be
sir.
knowing that there is a concept called as DFT, but you may not go in-depth roots of it to understand why and what where it is happening. That's where this training will help you. Okay.
No, sir, I mean to say that the candidate has enough amount of in-depth knowledge about the DFT field, DFT architecture, its implementation, where it is implemented and all. Like he has enough of the lexical knowledge. I mean, bookish knowledge. He has enough of it in terms of in the field of DFT. But
It's not
he
sufficient.
doesn't have
No.
some like
Bookish
experimental
knowledge.
sessions and
No,
what
no.
say experimental
That's
session
what
and
I'm trying to
hands-on
tell.
some tools.
The
So in
bookish
that
knowledge
case,
is
it
not
is
sufficient.
risky.
Abhi, you're breaking in between. I don't know whether you're able to follow my voice or not. The bookish knowledge is never sufficient in any industry to get a job until unless you are placed in the campus placements.
Okay.
Did I make it clear?
Yes, sir. Yes, sir.
That's it. If we are going for a campus opportunities and placements, that's a different story. The bookish knowledge is enough. If you are going to search a job on your own, where you want to get something on your own, you need some practical exposure, which you may not get it until unless you get a job. But yes, we are able to provide and we are going to support it through this course.
Okay, sir. Thank you.
Yes. Yeah. Any other questions from anyone else?
After that, any age problem is there to study this course?
See, it depends on company to companies where people would be asking. Some people ask like, okay, we want, they would be keeping some criteria like a minimum of 2018, 2017, or 2019 graduates only we will be taking. I mean, the maximum criteria. And some people would say like, okay, we are allowed to take immediate freshers who are passed on in 2022 and 23. So based on the company opportunities and their requirements, it would be there. But we have seen something like so far 2016, 17, 18 people are also placed like last year and like that. So some 5 to 6 years, I would say it is really tough, but it is givable try where you can give a shot. That's what I would say. So 1 2 years 3 years it is okay. So more than 4 years it may be little difficult, but it is, I would not say like it is not possible. It is possible.
Same to other domain also.
Yes, even through other domain also. Yes. Okay. Okay. I hope to see you again, all of you, in the actual course when I start for the regular sessions. I hope there are no more other questions. If you have any also, please do let me know. I will be able to answer them. Okay, good then. I can take it as like there are no more questions. Thank you everyone for your time. I'll close the session for today. See you.